An excellent application for logarithms is earthquakes, and the way we measure earthquakes, or at least the way we used to, something called the Richter scale. It's a scale that's based on logarithms that helps us better to understand earthquakes. Let's take a look and see how the Richter scale sort of works. It lets us compare the magnitude of an earthquake to the amount of energy that is related to that earthquake. So let's take a look. So what happens is that on the Richter scale, we rate an earthquake with a number like 1 or 2 or 3 or 4 or 5 or 6, something like this. And but the energy associated with the earthquake is over here. And what we can see is that, oh, sorry, this is not the energy over here. This is the number of earthquakes that we get at this particular magnitude. Over here is the energy release, okay? So what happens is when we're looking at earthquakes, we tend to call them, it's a 2.0 or a 3.0 or 4.0, or God forbid, a 7.0 or 8.0. And this is the amount of energy that's released. And for our purposes, to make it easier to understand, it's written in terms of the equivalent amount of energy if you explode, if there was an explosion. It doesn't say exploding what. I'm thinking it could be in terms of TNT, maybe 123 pounds, 4,000 pounds, 12,000 pounds. Notice by the time you get to a 5.0 earthquake, you're at about 4 million pounds of explosive energy. So again, the logarithms give us a way to express very large numbers, especially numbers that grow very quickly, with some relatively straightforward numbers, integers, whole numbers that we're used to. So anyways, this particular equation relates the magnitude of the earthquake with the amount of energy. So let's say that we have an earthquake and we know its magnitude, and the magnitude is equal to, well, let's look up a recent earthquake that's been pretty big. I'm going to pause. So maybe some of you folks might recall a large earthquake that occurred near Japan in 2011. It was a magnitude 9 earthquake. And one of the big problems with the earthquake was that it occurred near the Fukushima nuclear power plant. And so the result was horrendous. I'll leave that to you to look that up for more details, but we're going to focus on the idea that it was a magnitude 9 earthquake. And we're going to go ahead and use some math to figure out that if we had a magnitude 9 earthquake, how much energy is that equivalent to as far as explosive energy? So let's go ahead and do some math here. So we'll say that log of E is equal to 11.8 plus 1.5 times 9. That's what our M is, our magnitude of our earthquake is 9. So we'll use a calculator and do some math, and then we'll see what we get. So what I came up with was 25.3. And then we're going to do, there's actually a couple different ways to solve this. The first thing we're going to try is, you'll notice that it's log with no base, so that means log base 10. And I'm going to try to use the old Weingarten rule. I'm going to convert this from a logarithmic equation into an exponential equation. And the way we do it is this. We take this little base 10 and we raise it to the power of 25.3, and then we say that must be equal to E. That's it. It's that simple. 10 to the power of 25.3 equals E. In other words, 10 to what power equals this? So I don't know if you guys are really good with scientific notation, but if you are, then right now your jaw should be dropping. Because look at what this number is. It's 10 to the power of 25. Forget about the 0.3. 10 to the power of 25 means like what? Like 1 followed by 25 zeros? That's crazy. That's insanity. Anyways, that's a pretty big number. And again, that's why we use logarithms, because we can talk about the earthquake in terms of being a 9 instead of an 8 or a 7. And it's a little bit easier to understand than 10 to the 25, which most people just won't get. Anyways, you'll notice that solving this equation went pretty quickly by using the Weingarten whirl. Even so, I'm going to show you another alternate technique to solve the same equation. Okay, to me, this thing that I'm about to show you is the coolest thing. It's a technique called exponentiate. That is a fun word. I recommend that you try to fit it in at the next party you go to. Anyways, what exponentiate means is this. It means we're going to make each side into an exponent of some base. Now, let's see why we're going to do that. It's because we have this property of equality that says this, that if I have some base, b, raised to the power of x, and it's equal to some base y, or some power where I have another base b raised to the power of y. In this case, when I have two powers that are equal and the bases are the same, then the exponents must be equal. In other words, x must equal y. Okay, we've used this before to solve exponential equations. If we have this equal to this, we get this equals this. Well, now we're going to go backwards. We're going to pretend like we have x equals y, and we're going to go ahead and make the x and y into exponents of the same base. So here's what we're going to do. We're going to write a big base. In this case, because it's log base 10, I'm going to make my base 10. And then I'm going to make the exponent log of e. And then I'm going to set that equal to, again, base 10 raised to the power of 25.3. So hopefully you can see what I'm doing here is I'm just taking this x and this y, and I'm just turning them into exponents of a base 10. Now, why did I do that? Because there's this really cool thing that we can do. We can cancel this log with this 10 because it's a base 10. If this was not a base 10, it would not work. But since this is a base 10 logarithm, we can go ahead and just cancel those guys. And when we do that, what we end up with is simply e. And that is equal to, and then we say that's equal to 10 to the power of 25.3. So where did this come from, this idea that we can just cancel those guys? Well, it turns out it has to do with the idea that these guys are inverse functions. And so what happens is when we apply one function to another and they're inverses, remember that whole thing about f of g of x? For inverse functions, if we do the composition of functions, we should just get x. And if we do it the other way, same thing. We should just get x. And so it turns out, if I have some base and I raise it to a log of the same base, and there's an x right here, these guys just cancel and I just get x because of because it's like doing f of g of x. And then it turns out the other way around, we can do that as well. We can also do, if we have log base b of an exponential with a base b to the power of x, this guy, again, we're just doing things the other way around. If this is f of g of x, then this would be g of f of x. And it should also just give us x, okay? Because again, this log base b and this base b, they cancel. All right, so this lets us do some really cool things. It means that if we have something like log base 3 of 3 to the power of 1, well, we get 1. If we have log base 3 of 9, we get 2. We sort of already knew that, but I'm just going to rewrite it for you in a new way. Log base 3 of 3 to the power of 2, These guys just cancel. That's why we get the 2. That's another way to look at it. Kind of interesting, huh? And that means that if we have all kinds of wacky stuff, like if we have something like log base 3 of 3 raised to the power of 2y minus 7, okay, then guess what? These 3's, the 3 and the log just cancel, and we get 2y minus 7. Nifty, huh? Anyways, hopefully in class tomorrow we'll get to use this and practice this. And again, remember, this is just this idea of exponentiating in order to solve the equation, which is what we did here, is just one way to get the solution. You still have the option of using the Weingarten whirl and getting the same thing. It'd just be nice if you knew both, because I will be asking questions on the test that discuss the inverse nature of logarithms. It'd be nice if you knew what they were. Again, it'll be easier if we practice this a little bit in class.